In this example, we demonstrate a simple but very common vehicle attack that has cost the automotive market millions over the years, and that is mileage tampering. Using the Secure-CAV demonstrator setup, you can see that our Carla vehicle simulator is being used to generate irregular vehicle telemetrics, which are in turn sent over the physical CAN bus that we've rigged up in this system. A virtual vehicle instrument cluster made up of a RISC-V processor along with our Tessent embedded analytics technology on the FPGA board is used to intercept the CAN bus traffic and display the data as per a normal dashboard onto the second screen as shown. The main data in the display is the engine speed along with the actual and corrected odometer values. You can see during normal operation these values are the same. We then engage a commercially available mileage tampering device. This manipulates the CAN bus traffic being sent to the dashboard. However, the Tessent embedded analytics monitors that are built into the virtual dashboard are able to detect that the CAN bus data is being filtered and is able to make corrections. Therefore, you can start to see that the actual odometer values on the bottom left and corrected on the bottom right are now different, showing the results in a vehicle both with and without this type of hacking detection and mitigation. This example just starts to show how the embedded analytics technology deploys real-time detection and correction of data corruption. Please take a look at some of the other abuse cases to see other more advanced applications of this technology in action. The OBD2 interface is available within almost all vehicles today and gives direct access to the vehicle's internal network, enabling any attacker to easily inject malicious and harmful code to disrupt the vehicle system. Even when encrypting the data over the OBD2, there are various ways to still extract this data being sent to the various vehicle ECUs. In this example, the OBD dongle is attached to the demonstrator's network. Then, using a third-party application, it is possible to send various requests over this dongle to the vehicle systems. The Tessent embedded analytics in this case is monitoring all of the CAN data traffic and is able to characterize each frame as either harmless or harmful. A harmless packet is where the request for data is made to one of the vehicle's ECUs. A harmful packet is one which is making a request to activate a specific function. In the case where a harmful packet is detected, it is possible to see the demonstrator's response where a warning indicator is displayed on the virtual dashboard. At the same time, we can ensure that this packet is either blocked or disregarded such that it doesn't impact the car's safe operation. As vehicle functions and systems become more and more integrated, the risk of attack is no longer just at the vehicle network level, but also within the vehicle system's architecture itself. In this example, we use the vehicle's infotainment system, which is fully integrated with other systems within the vehicle. Through the system-on-chip interconnect, the infotainment system has access to main system memory or peripherals. If the attacker was to penetrate the infotainment system, they could potentially be able to gain access to those shared vehicle resources, changing memory contents or maybe reconfiguring peripherals. Here, the Tessent embedded analytics technology provides monitoring that is completely independent of the system's software, so that it could not be tampered with, even if this software was reprogrammed by an attacker. The monitors are checking every transaction on the internal AXI bus and are able to identify attempted forbidden transactions, for example if the infotainment system is accessed in the main system memory. Here again in this example, when we trigger these forbidden transactions, you can see the notification that they have been detected by the Tessent embedded analytics monitors via the flashing icon on the virtual dashboard. As a more specific example of how gaining access to a vehicle's internal systems can have an effect, this use case shows how a simple door lock, which although independent, is still controlled by the vehicle's central processor and software. As with the previous example, the attacker is able to gain access to the main system's AXI bus architecture and essentially access an address range that can be used to activate the door lock mechanism. Whereas in the previous example, we used a straightforward bus monitor on the Tessent embedded analytics configuration, here we use what we call a bus sentry. As opposed to being a passive monitor, the sentry is able to directly block these types of transactions without any additional checking or intervention. So in this case, you can see when the attack comes and the icon on the virtual dashboard flashes where the bus sentry is blocking the memory access. As you can imagine, our attacker will try and attack the vehicle from many different angles to try and avoid any built-in security protection. In this example, the attacker gains access to the CAN bus and tries to initiate a TCU software update over the CAN bus infrastructure, essentially performing a man-in-the-middle type attack. However, the embedded analytics AXI monitor can detect illegal accesses to the TCU memory from a forbidden source. Then, using the CAN sentry, the embedded analytics can block the appropriate CAN packets which are the source of the attack. As with the other attacks, when this is initiated, it is possible to see the warning icon flash on our virtual dashboard to show that the attack has been blocked. The system can then reset to a normal state. When reviewing the different types of cybersecurity attacks on a vehicle, we also have to assume that the vehicle could have been physically compromised by our attacker by adding or changing vehicle components. So having multi-layers of security is the way to ensure against this. In this example, we have a TCU that has already been compromised. However, we can still guard against this TCU issuing any commands that may put the vehicle or its occupants in danger. Here we are able to have the TCU issue an engine service mode request, which would be extremely dangerous if the vehicle was in motion. However, with the Tessent embedded analytics, we are able to detect that this request has been issued while the vehicle is in motion, so we can block this CAN packet with the CAN sentry. Again, this detection can be seen on the virtual dashboard.